In addition to a variation in time, it turns out that you can also have a variation in distance when you are going near the speed of light. And so here we're going to talk about a relativistic length, also known as length contraction. So your book goes through a lot more detail on the derivation of this equation, but basically you have two objects. The distance apart would be your proper length, but if you are moving at some velocity v, then their relativistic length would be equal to the proper length times the square root of 1 minus v squared over c squared. In other words, L is equal to L naught over gamma. Now just let me explain the difference between proper length and relativistic length a little bit better. Let's say that you have two planets, planet 1 and planet 2, and you're just sitting out here out in space watching that. So you're moving at the same velocity, same rate as those two planets. Then you measure that length to be the proper length because you are in the same reference frame as the planets. Now, if you have some spaceship here that's moving off at some high velocity v, close to the speed of light, then the ship is not in the same reference frame anymore as the planets, and so the ship measures that distance between the two planets to be L, the relativistic length. And that relationship is, as we talked before, the relativistic length measured by the ship would equal the proper length measured by someone who's in the same reference frame as the planets divided by gamma. Now, that means that now we have variations in both time and space. I kind of hinted on this in the time contraction video, but that means that now space and time are more intricately connected since we have both relativistic time and relativistic length. And so while space has 3 dimensions, time is a 4th dimension. And so when viewed from different reference frames, the space and time coordinates can mix. So no longer is time just a reference point that connects space. It no longer can connect space because it itself is a variable as well. Let's go through and do a quick example of both time dilation and length contraction. Let's say that you're an astronaut traveling near the speed of light at 97% of the speed of light, so 0.97 c. You're traveling from Earth to Jupiter, which is a distance of 780 million kilometers. In the middle of the trip, you measure the distance between the Earth and Jupiter. What is your measurement between Earth and Jupiter? Okay, so what are we given? We are given that the velocity is 0.97 times the speed of light. And we are also given the distance from Earth to Jupiter. Which distance is this? Well, this is a pre-known distance, so this would be a proper length. So 780 million would be 10 to the 6th kilometers. Okay. There we go. That 6 looks better. And so how do we find the relativistic length? Well, that's just going to be the proper length divided by gamma. Okay, so we need to come over here to the side and actually find gamma first. So here's gamma, 1 over the square root of 1 minus v squared over c squared. So that's going to be 1 over 1 minus v was 0.97 times the speed of light, and that whole thing has to be squared, divided by c squared, and take the square root of that. The c's will cancel, so you're left with 1 over square root of 1 minus 0.97 squared. And that is going to give us a gamma value of 4.11345. So that means then that our relativistic length that you measure between the Earth and Jupiter will be your proper length, which was 780 million kilometers, divided by gamma, 4.11345. And that gives you a length of 190 million kilometers. Basically, from your point of view, because you're traveling near the speed of light, it appears as if the distance between Earth and Jupiter has been cut to 1/4 of the actual distance. Okay, so that is going to be your measurement of the distance between Earth and Jupiter. So next question is, how long does it take you to get to Jupiter? Well, this one is just a simple equation. So here you are, there's Earth, here's Jupiter, and you're traveling at your velocity v, where velocity is your distance, which is the distance you travel, which from your point of view is the relativistic length divided by the time that it takes you. But since you are in the ship and you are the one who has the clock in the ship, you're in the same reference frame as the clock, therefore we need to talk about the proper time. So when we ask how long does it take you to get to Jupiter, we're talking about the proper time. So the proper time would then be the relativistic length divided by the velocity. So we just found that the relativistic length is 190 million kilometers divided by your velocity, which is 0.97 times the speed of light, which is 3 times 10 to the 8th meters per second. Now be careful here, because here you've got kilometers, but here you have meters. So you're going to need a unit conversion in there as well to go from kilometers to meters. And then everything will work out, and you end up having a proper time of 652 seconds, which if you convert that to minutes, it's about 10.9 minutes. It would only take you just shy of 11 minutes to make it from Earth all the way to Jupiter. But then that begs another question. How much time has passed at mission control during your trip? Well, we have two ways of finding this out. So I'm going to divide this in half. The first is just like we saw before, velocity is equal to distance over time. But in this case, mission control measures the distance from Earth to Jupiter as the proper length divided by the time that passed at mission control. Sorry, yeah, that's right. The time that passed at mission control. You are now in a reference frame outside of the moving object, the spaceship, and so we're dealing with relativistic time. Okay, so that means that the amount of time that passes would be the proper length divided by the velocity. The proper length is given in the problem is 780 million kilometers divided by the velocity, which is 0.97 times 3 times 10 to the 8th meters per second. Again, we have that same issue. We're dealing with kilometers on top and meters on the bottom, so we have to convert the kilometers to meters. And when we do that, calculate everything, you get that it took 2,680 seconds, which is equal to 44.7 minutes. Now, the other method to do this is using the proper time that we got from here. So we got 652 seconds. So if I use the relativistic equation, that the relativistic time is equal to gamma times the proper time, Remember that gamma is 4.11345 times 652 seconds would give me a time of 2,680 seconds, which is 44.7 minutes. Exactly the same answer, so it works both ways. Bottom line, even though from mission control, you measure a distance of 780 million kilometers, because you are traveling at 97% the speed of light, that length has contracted relativistically, so it appears as if it is only 190 million kilometers. And even though you make that journey of 100 million kilometers in 10.9 minutes, in reality, the amount of time that's passed on Earth is 44.7 minutes, over about 4.5 times as long. No, it's right around 4 times as long. And so that's how you apply and use the time dilation and length contraction equations and find out relativistic changes in both time and distance.